In this video, we're going to look at the structure of MOSFETs. The diagrams are out of our textbook, Electronics Technology Fundamentals by Paynter and Boydell. So MOSFETs are very different structurally than JFETs. If you remember, a JFET has a PN junction, although it's always reverse biased, so current is minimal, gate current is very small. MOSFETs go one step farther as far as minimizing gate current to practically zero, and you'll see that because of the structure. You'll see why. There is no PN junction between the gate and the rest of the device. If we look at the structure, you can see there's a metal gate, and then there's a silicon dioxide layer, which is an insulator sitting right through here. So the gate is insulated from the rest of the device. So essentially no current at all. We've said JFETs were somewhat zero current, voltage controlled devices, but there is some current that flows through a reverse bias junction, PN junction. But here you can see we've improved on that. And I think you can see for MOSFETs, no junction exists at all. That does make them susceptible to static voltages, so they can be damaged easily from static voltage because it can build up on the gate and then punch through the insulator and damage the device. So whenever you see electronics that are sensitive to static electricity, it's because there's MOSFETs in there. So we have the gate, which is just metal, and then we've got the insulating layer, and then you have the actual channel that current can flow through. It'll flow from drain to source. Conventional current will, if it's an N channel. This example that we have, there you can see the N, is an N channel MOSFET. And even more specifically, it's a D-MOSFET, a depletion type MOSFET. So D-MOSFET, N channel, that's our example. Here's the schematic symbol. Later we will look at the E-MOSFET, and you will see a difference in the schematic symbol that relates to the structure. I'll say for now, the D-MOSFET, as it sits by itself, a channel does exist, and you can see that. Look, the drain down through to the source, there's a path that exists, and that's, you can see in the structure too, I think, that the drain has a path to the source through the N channel. For the E-MOSFET, that's not going to exist on its own. And you'll see that in the schematic symbol. There'll be openings here and here. I always tell students, if you have a hard time remembering these schematic symbols or you need to draw them, just understand this structure, and then when you want to draw an E-MOSFET, just get out your eraser and erase a little bit of the channel here and here, because a channel does not exist in an E-MOSFET as it sits by itself. All right. So you have the N channel, and then you have what's known as the substrate. It's built upon some P material here. And okay. Just a few finer points to mention before we move on. With the structure, it is a 3-pin device. There's, the drain, the gate, and the source. And being an N channel, it's going to flow conventional current, like we said, from here to here. I think I remember reading somewhere that fundamentally it could be a 4-pin device, and maybe some of the early FETs might have even been. There would be a drain and a source and a gate, and then the substrate could be another point on the device. But the ones I've seen are all 3 pins. The other thing, trying to remember, but I think here's the way it oftentimes is. The source is oftentimes, there's a connection to the substrate. I don't know if this is quite right, where the drain looks like it has a connection to the substrate. I'd almost want to scoot that drain over here a little bit and not have it touch the substrate. And the reason I think that, or I'm thinking that way, I remember what's called a body diode for MOSFETs, and by that it's this p-n junction that exists, and if you look at it, you could go from source to the p-type through the n-type back up to the drain. I only mention that because you're going to see that on schematic symbols. Oftentimes they'll draw a diode from here to here, and I don't know how well I could freehand that. I can try for you. So it would be something like this. Oh boy. And here we go. And then this is what they would call a body diode. And it is built in to the MOSFET. And so some data sheets will show that. So don't be thrown by that. That's just letting you know that the way they've put the thing together is like I described, where maybe the drain does not have a connection to the P substrate, but there is a PN path back to the drain from the source. Why am I making a big deal of this? This feature of MOSFETs is oftentimes used on purpose. They have the body diode be the freewheeling diode. So for high-speed switching, I can use a MOSFET to turn something on, and when I turn it off, the kick that I would get can be freewheeled backwards through the body diode. So you don't have to have always a freewheeling diode added. Very convenient. And especially if you're using something like pulse width modulation, high-speed switching, the body diode might take care of the freewheeling, the need for that. We mentioned this example is an N-channel D-MOSFET. A P-channel, you can probably guess. The channel would not be N-type, it would be P-type. The substrate would be N-type. The schematic symbol would just be this little reversal here. The arrow would be pointing out. This arrow does indicate the PN junction. You can see for the N channel, this arrow, if you think of it as a diode type arrow, then it's in the correct orientation, P to N. And so obviously for a P channel, it would just reverse. I should mention too that the MOSFET simply gets its name from M for metal, right? And then the oxide layer, and then silicon after that. So it's metal, oxide, and silicon, where we abbreviate it as MOS, and then FET. Maybe there's an older name, I think, IGFET, which stood for insulated gate FET, which again is the big attribute that sets MOSFETs apart from JFETs. JFETs are junction FETs. There's an actual PN junction. We use it reverse biased, but it's a PN junction that's actually there. And then MOSFETs or IGFETs, they have the insulated gate. MOSFETs are voltage controlled, just like JFETs. The whole FET family is voltage controlled devices where gate voltage controls drain current. And we can see here for the N-channel D-MOSFET example that we have, if we apply 0 volts to the gate, VGS is 0. You could just set a supply to 0 or very easily just short the gate to the source, as you can see here. So there's no voltage on the gate. And this would be what the structure would look like, just what we had seen previously. There is an N channel that exists with 0 volts on the gate. And conventional current will flow down through that channel, right down through here. The D-MOSFET is called a depletion MOSFET because we can narrow the channel. And you'll see with an E-MOSFET that's not the case. But here we are with our D-MOSFET in depletion mode. For an N channel, the way it would work is we're applying some negative voltage to the gate. When we apply negative voltage to the gate of an N channel D-MOSFET, it's going to repel electrons near the gate. And those are the majority carriers in the N-type silicon. So you're basically depleting this region in here of majority carriers, which are the electrons. And that narrows the channel. So it's basically like charges repelling. There's no current. It's just the voltage at the gate being negative, pushing away electrons on the other side of the gate in the N-type material. And you can see it narrows the channel. And again, the channel is going to be running right down through here, conventional current. For a P-channel D-MOSFET, you would apply positive voltage to the gate to narrow the channel. Probably could have guessed that. The channel on a D-MOSFET can also be widened or enhanced. You would just apply some positive voltage to the gate with respect to the source. That is going to attract majority carriers into the N-type. It's going to sort of push back the P-type region, I guess would be a simplistic way to put it. But it's going to widen the channel. So D-MOSFETs, although in their name they're known as depletion capable MOSFETs, it kind of doesn't tell the whole story. So the D-MOSFET has a channel as it sits by itself that can be narrowed, depleted, or widened, enhanced. They can do both. When we get to the E-MOSFET, it can only be enhanced. And if you think back to the JFET, it can only be depleted. So a JFET's depletion only type device. A JFET is a depletion only type device. An E-MOSFET, which we'll look at in a minute, is enhancement only. And the D-MOSFET is the one that can be depletion or enhancement. Channel can be narrowed or widened. And here's the example of an N-channel D-MOSFET. The channel being widened by putting positive voltage on the gate. Again, if it was a P channel, putting negative voltage on the gate would widen the channel and increase the conventional current flow. For an N channel, of course, conventional current's going to be running like this. Woo, got a little crazy there. Oh my goodness. And I think you know, just from what we talked about with JFETs, this being an N channel, well, for a P channel, conventional current is going to run the other way. If it was a P channel, conventional current would run from the source up to the drain. Of course, this would have to be reversed, right? We'd have to reverse that power supply. And so everything reverses. Yeah. Which is why for this example, we're just picking one. The N channel and following it through. I'm not really helping with that, am I? I'm jumping over to the P channel. But the original thought was pick the N channel and stick with it to get you up to speed on the structural, looking at the structure. So that we don't get too dizzy going back and forth. Like I said, I kind of ruined that a little bit.